Okay, so the one thing I'd really like you to think about with the absolute values is what happens with inequalities involving absolute values. And I'd like you to consider the expression when you have x minus h. Think of it as the distance between x and h, okay? Now, of course, we have a value, we take a difference, and on a number line, you know, we get the number of spaces in between the two values. But let's say I was measuring this table. If I measure this table, let's say it's 6 feet long, okay, and I measure it from right to left. If I take my measuring tape and measure it from left to right, I wouldn't tell you that it's -6 long, right? I mean, you just don't use negative numbers as a measure of length. And so we're going to use distance as always a positive number. It's a size of something. It's essentially what we're doing. So if we have, let's say, an expression, an inequality, the absolute value of x minus 2 is less than 1, think about this as whatever value of x is, the distance has to be less than 1. And so here we're looking at an interval that's within 1. So the center of this value is the 2. So whatever value of x I'm going to choose, I have to make it less than 1. So if I use, for instance, 2.5, I'm going to get 1/2 is less than 1. That's fine. If I use 1.0 or 1.5 or 3/2, what I get in my expression is I'm going to get -1/2, but my absolute value is going to change that to a positive number, and so 1/2 is less than 1. And so really what I'm doing here is I'm saying what the physical meaning of this particular inequality is like x is less than 1 unit away from 2. Okay? So the absolute value, when you see a difference in there, always think of that as the size of something, because the absolute value is discarding the direction or the orientation of that number, is just looking at what's its size. Now, of course, the classical way to solve this is that we break this up into two different inequalities. And so we see that we take the x minus 2 is less than 1, and then when we remove the absolute value the other way, we have x minus 2 is greater than -1. Remember, we flip the inequality and change the sign of what's on the outside, and so we get this thing where x is less than 3 and x is greater than 1. Now, think about what this means if you're within, if this is x minus 2 within 1, okay, what that's talking about is that both conditions have to apply. So if I, let's say, if this room is perhaps 30 feet wide, and if I say, okay, whatever is within this room, it has to obey both rules, that it's on this side of this wall and it's on this side of that wall. Okay, so this is an and. It has two conditions that it must meet. Yes, you had a question?
I'm sorry, but after, can you go back to the previous slide?
Yeah. Let me finish the thought first, okay? So when we have less than 1, we're looking at within. Now if we say greater than, that means you want the distances further than a certain value, so it's outside of that. And so if we're looking at the distance from me to the wall, and I want that to be greater than, it is either outside this way or outside that way. So with a greater sign, you have an or instead of the and, because either condition can apply. Okay, so let's go back to that last slide. Did you have a specific question, or you just didn't quite finish writing everything? Okay. Okay, how's that? It's good? Okay. All right, so I'd like you to try this one. I want you to solve this and graph it. Should be a fairly quick exercise here. Okay, so while you're finishing that up, a few of you came in late. I was announcing some extra credit. Go to this, look for this poster in the hallways. There's going to be a talk by Professor Connor on Monday at 4 o'clock. And if you write a note to me as to what he said, then we'll drop the lowest quiz. Okay? All right, anybody get this? What'd you get?
2 is, x is greater than 2 and less than 2.
Greater than 2 and less than 2? I don't think so. Less than 4, yeah. Okay, so here's the solution. So you write the inequality. First, you just take off the absolute value sign, and then the next one you take into account the case where the absolute value sign is going to change the sign of the expression. So we'll say less than or equal to -3, and then adding 1 to both of those, we get x is greater than 2 or x is less than -4. And so if we graph this, what we get is 2 different intervals, one that starts at 2 and goes greater than 2, and then the other one that starts at 4 and goes less than 4. Now, with this notion of the distance again, look at this value in the middle. This is x plus 1. So remember, the distance is a difference. So if we say, instead of x plus 1, if we say x minus a -1, then we'll find that the center of this thing is at -1. So the way to look at it is that even though it's a sum, look at it as a difference, because if you look at it as a difference, then you can use that first part as saying, okay, that absolute value expression means the distance from x to -1. And then the rest of the expression will say is greater than or equal to 3. So just like being outside of this room, you know, it's either on one side or the other, but a value is never two, it can't be on both sides of this interval at once. So it's an or. Okay, so any questions on that? Okay, so now let's shift gears and go to a power function. And so what we're going to call a power function is a function that's of the form where you have f at x equals x to the something. Okay, we'll call this p. And we're going to refer to x as the base of the expression. So the base is a variable, the exponent is a number. So that's different than saying something like 3 to the x. Okay, those are exponential functions, and you'll deal with those in Math 14. But right now we're going to deal with the variable in the base, which is x to the p, and p is any number. Okay, so we can have, p can be 2, so we have x squared, or p can be 3, or 5, or 7, or any of those. But we're going to call it, you know, this form a power function. So if you have it of the form where you have the base as a constant and you have x as the variable in the exponent, that's next semester. We're not going to deal with that here. So we have 2 functions in our toolkit function that that is like this. The first one is just x squared, and then the next one is x cubed, and they behave differently. So we're going to look at the behavior of these things, and for now we're going to deal with just integer exponents. Obviously you can have any real number as an exponent, but that has some consequences that are a little different than what we're going to talk about here. Now, I suppose, strictly speaking, the linear function f at x equals x is also a power function because the exponent is 1. And so that, you know, we can consider that a power function. We usually consider that a linear function, but it does, strictly speaking, follow the definition of our power functions. Okay, so I think here. Now, I have a bunch of graphs here, and they're all kind of superimposed. The green one is x squared. So this is that parabola that we've been looking at. If you look at x cubed, that's the blue one, and you can see that this thing, comes up to 0 and then goes beyond and goes off as high as you want. Now the next ones involve either even numbers, like this x to the fourth. Look, it intersects this graph. They all intersect right here where we have -1 and 1, and here we have 1 and 1. So if I were to, just start from scratch in drawing these, if I take f of x equals x squared, then from the standpoint of looking at 1 and -1, I'm going to have these points. Now if I look at another function, g at x equals x to the fourth, I still have the same 3 points. But what's going to be different about them, when you're greater than 1, x to the fourth gets bigger faster, right? So 2 to the fourth is bigger than 2 squared. But when we're talking about numbers in between 0 and 1, it's going to stay closer to 0 longer. So what I mean by that is, if we say 1/2, so if you say f at x to the 1/2 is going to be 1/4, right? Because 1/2 is 1/2. So this is my f at x point. But if I say x to the fourth, so 1/2 to the fourth is going to be 1/16, and so it's going to be down here like this. And so rather than having our parabola like this, what's going to happen is it flattens out a little bit towards the bottom, and then after it goes past 1, it increases faster than x squared. So we're getting this thing where we're kind of making this more blunt. Now the same thing happens with the odd numbers. Basically you get this kind of effect again, except we're coming up from this direction where we have 1 or -1 and -1 is common to all of these. But if x cubed is like this, then x to the fifth is going to go to 0 faster, and then level off at 0, and then do kind of the same thing that x to the fourth does here. So we have this flattening kind of effect where if x cubed is like this, maybe x to the ninth looks a whole lot like this, where this area is flatter, closer to 0. And of course that continues with all of your odd numbers. Now, so we look at the even numbers, and the even numbers, we're going to talk about long-term behavior on this thing. So when we go to smaller and smaller numbers, so we go -1, -2, -10, -100, and all this, it's going, and when we have an even number in the power function, it's going to be positive, and it's going to go to infinity. When we have an odd number for the exponent, it's going to go to -infinity. So the long-term behavior on the right side of these things is the same. As x gets really large, f at x goes close to infinity. On the negative side, if we have an even number, then it goes to a positive infinity. If it's a negative number, then it goes to a negative infinity. So that it's in the negative side where we have the change in behavior. Okay, and I think I just finished labeling these. Okay, tiny type. So this is what I was just saying, with the even exponents, x increases, f at x increases. And when x is less than negative, when x decreases, f at x increases. Now with the odd exponents, as x increases, f at x increases, and as x decreases, then f at x decreases as well. Okay, so we did, I did talk about the even and odd. This is easy to remember now because you know from the toolkits what x squared and x cubed is. All the odd numbered power functions behave in kind of a similar long-term fashion as x cubed. All the even ones behave in a similar fashion to to x squared. It's just a question of how flat is the curve close to zero. Okay, so it increases its kind of flat spot. Yeah, sorry, that was a little fast. Okay, how's that? All right, so now we're going to shift to something called a polynomial function. I think all of you have seen polynomial functions. What a polynomial function is from the definition that I'm going to give you here is that it's the sum of power functions. Okay, so I can write this in two different ways. You've probably seen this written in the opposite order, where we have first a constant term, and then a linear term, and then a squared, and so on, until we get to our degree. So let me give you a specific one here. So we call these things terms. Now the term, the second term is negative x cubed. The negative always is part of the term. So think of these things as the sum of power functions, and so it's possible to have a negative coefficient in front of one of the power functions. So here we have a couple terms. This has a total of 4 terms. The highest term is what we call the degree, or the exponent with the highest number is the degree. So in this case, this is a 4th degree polynomial. So out of the term that has the highest degree, we call that the leading term, and we'll also call that 3 the leading coefficient. Okay, so whenever we're referring to leading anything, we're talking about the term with the highest degree. Now it turns out that this is quite significant, the leading term, because even though, you know, if we compute a small number like, let's say x equals 1/2 or x equals 1 or 0 or something like that, all the terms kind of play in fairly equally. You know, you can't discard any term. But the long-term behavior of these things, when x is very large, then it's just the leading term that determines its long-term behavior. Okay, so think about why that would be so. Let's say x equals 100. Okay, so the first term is going to be 100 to the 4th power. So that's a 1 with 6 zeros behind it. The second term is going to be 100, did I say 10 or 100? 100 cubed. We're going to, oh, then we're going to have 6. We're going to have 8 zeros in front of the, behind the first one, 6 in the second one. So already the second term is only 1% of what the first term is. And so as numbers get really big, the leading term is the one that dominates. Okay, so everybody up with me on this? So the coefficients include the negative sign. So let's look at the behavior here. I already said one behavior. The long run behavior follows the long run behavior of the leading term. Now, of course, if we have a negative in front of it, these things, you know, we have this, this reflection that happens. So we, instead of positive values, we get negative values, and instead of negative values, we get positive values. So it's rotated about, the leading term is rotated about the x-axis, even though, you know, this thing is not either even or odd. So we're going to expect the long-term behavior of this thing to be similar to x cubed, or 3x cubed. So as x go, now here's some new symbols here. As x goes to infinity, and just read that arrow as it goes to, f at x goes to infinity. As x goes to negative infinity, we're going to expect f at x going to negative infinity as well, because we have an x cubed term. Now, the short run behavior, this is going to correspond to the intercepts. Now remember what an intercept is. It's where it crosses one of the axes. And so we have either crossing the y-axis when x is 0, but then we also have some values of x where f at x would be 0. And so depending on where those zeros fall, that's going to really determine what the short run behavior is. What's the behaviors close to 0? And so with the two intercepts, the first one is fairly easy to calculate. F at 0, all the terms that drop out because you have an x in there and you just have the constant term left over. The x-intercepts, what you do is you set your function to 0, and what you'll have to do really to get these is to factor it. And so I factored this, and so it turns out that we have 3 zeros here. We're at 1/3, at 3, and at -2 it's going to be 0. So let me see what I already know about this if I just graph what I know, and then we can make some inferences. Okay, so at 0 we know we're going to be at 6. At x equals 1/3, we're going to be at 0. At x equals 3, we're going to be at 0. 1, 2, 3. We're going to be at 0. And at -2, we're going to be at 0. So this is going to be -2. Okay, so now what we do is we think about what's the long-term behavior of this thing. All right, it's, we have a positive coefficient. We know that's not going to change anything then. And if the long-term behavior says that as x goes to infinity, we're going to be off in this direction, and as x goes to negative infinity, we're going to be off in this direction, we know pretty much that the graph is going to look like this, in some fashion, okay? Now, it doesn't, what I'm not sure of, is this my maximum value, or is it going to peak somewhere before? We don't know that yet. We will find a way to determine that. But basically what we have is this thing kind of going back and forth through the x-axis. And so the part that I'd really like you to get from the x-intercepts now is and the long-run behavior is where it's coming from, and the fact that it's going to bob back and forth until the long-run behavior takes over on the positive side. So what's going to happen here is we're going to have a bunch of different criteria that are going to kind of give you clues about the function, and you'll be able to either visualize or sketch out a graph of what the function is. And so we're going to do this with several different kinds of functions, but this is the first one, the polynomial function, that just by knowing its intercepts and long-run behavior, we have some idea of what this graph looks like. Okay, so polynomial behavior here. The long run behavior follows the leading term. This is an odd power. The maximum number of roots is the polynomial degree. Okay, so if we have, in this case, we have a third degree polynomial, that means we have 3 or fewer roots. And by roots, what I mean is, what are the values of x that give f at x equals 0? Okay, so I'm looking at my x-intercepts. So when we have an x squared, you know, a quadratic polynomial, it can have at most 2 roots. A cubic can have at most 3. Now, the thing about the even numbers is that it's possible, like if you have x squared plus 1, there's no root, right? There's no value of x that you can put in x squared plus 1 that'll equal 0, right? Because the smallest x squared can be is 0, and 0 plus 1 is 1, so that's the minimum value. But it's not true with odd powers or odd exponents, because we'll have always at least 1, because we have to go from negative infinity to positive infinity, and so you can't go from negative infinity to positive infinity without crossing 0. All right, and that's one of our, we're going to see a theorem that's related to that, but the odd powers always have at least 1 root. And so what that means is that an odd power can always be factored at least into one term. It may not be a very pretty term. It could be, you know, something that involves a fraction or so, but it's a real number, and it does factor to that. Okay, so then the maximum number of turning points. And so we're going to call a turning point is when we turn around like this. Okay, so if we have, if we count the turning points, add 1 to it, and that is the minimum value of the degree. So if I were to just take an arbitrary function like this, okay, what this rule is saying is that I know what the degree is. Now I only have 1 root, okay, so that part, how many roots, what's the maximum number of roots, that doesn't help very much. But if I look at, I have 1, 2, 3, 4 turning points where I'm going from increasing to decreasing, and then decreasing to increasing, so there's a second turning point. Third turning point is when I'm going increasing to decreasing, and then, so I have 1, 2, 3, 4. This has to be of the form at least to the 5th. We know it's odd, and we know the minimum value of it is 5 because we have 4 turning points. And we'll see why that's the case when we talk about derivatives. So then what I've shown you there is that it's at least a 3rd degree polynomial because of both of those rules. Number 1 is because it has 3 roots, and number 2 is because it has 2 turning points. One where it goes from increasing to decreasing, and the second one is where it's going from decreasing to increasing. Yes?
Can you explain why it's 2 roots? Like, do you just, do you add 1?
How many roots?
Can you explain why it's 2?
Yeah, well, we have 2 turning points. Okay, so what I'm calling a turning point is when I'm changing my direction. Okay, so this one I'm increasing. So when I change to going decreasing, that's a turning point. Okay, I'm decreasing here, and then when I change to go to increasing, that's a second turning point. Okay, so it happens to be at these little bumps and valleys. Okay, so here's a turning point because I'm going the other direction now. Here's a turning point because I'm going the other direction. Here's a turning point because I'm changing direction. Here's one because I'm changing direction, so I have 4. And so if I add 1 to 4, I have to have a 5th degree polynomial, even though I only have 1 root. Okay, now on this case, we had 3 roots, and we knew it was I gave you the function before, it was a x cubed in there. So you know you have 3 you have up to 3 roots, and here we have our maximum value, but we also have 2 turning points. Okay? All right, so we're going to continue on Friday going through algebraic functions that we can make, with polynomials and with expressions. We're going to talk about rational functions and get into things like asymptotes and all that. When we go through all of our algebraic functions, then what we'll do is we'll come back to the discussion of functions and talk about inverses of functions, how to calculate them, and then also what an inverse of a function will tell us in terms of some of these rules. Now, any one of these particular rules, like the maximum number of turning points is the polynomial degree minus 1, those are fairly straightforward and fairly, well, I haven't proven that to you. I'm asking you to take that on faith that that's the way it is. But even the ones I'm going to prove to you, you're going to have perhaps a dozen or so of these kinds of rules. And it's going to be one of the things that I think most people find the most difficult about this class is that you have a lot of different ways to get information out of a function. And so, start keeping a catalog of these things. So when you see a rule like this, highlight it in your notes or, make some, accumulation of these things. And of course, we're going to have exercises that keep on going back to the things that we've talked about before. But this is really where you're going to do well in the first part of this course is if you can keep these kinds of things straight and try and develop some sort of intuitive understanding of them. Okay, so I'm going to be in my office